So here is a wind turbine, right? And I hope you can see the slope of the plate. So we said that the currency of extracting power in all those turbines, whether it's under, on top, in the air, or they actually have one that's they put it in the water for tidal wave, tidal power. Like there is current under, right? And it actually extracts a lot of power in the, because this, remember what's the input power? Half rho. What's the input power available for that turbine? Half rho A multiplied by V cube, right? So even if the water velocity is small compared to the water in the, compared to the velocity in the wind, the density, rho air is 1, rho water is 1,000, right? So mean 1 meter per second water is like 10 meter per second wind, as far as those turbines are concerned, right? So anyway, we were saying that how the currency of extracting power is angular momentum, right? So when the wind come or the water current come, if this guy is under the water, he will come straight, right? And the plate angle is such that when you come like this, he will go this way, right? He will twist, this guy will go this way, this guy will go this way. So you will see that when the air leave here, he will be twisting in that direction, right? The air will leave in a wake like this. So that will make the plate go this way, right? And if you notice, if you look at this orange, sorry, there's a green light over here. I think it's very hard to look at, but you see that? Do you see the light? Very hard to see, but it's light, right? So I do this demonstration for high school when they come to our campus. Like they put them 3 times last year, the semester. So when I was taking this from the HRC here to the main hall where we met them, and there was a little bit wind in the way, it actually rotated exactly in the right direction. I was so happy, right, that it works. Fluid mechanics works, right? So it has to rotate this way. Yes. And we remember how the plate is not twisted exactly at the same angle everywhere. Why? Because he's designed for not V absolute. The plate is designed for V relative. And why V relative here in this have different direction than this V relative? Yeah, U is different, right? So for the same V, U here is small, U here is big. So that the tip here will feel as if the flow is not coming this way. It feels as if the flow is coming with a really big angle. So at the hub, he's coming, expecting the wind to come straight toward him. But at the tip, he expects the wind to come with a big angle. So he needs to orient for it. So here you're like this, here is like that. Right? Very good. So, and one more thing before we leave. So now we said that for optimum performance, that plate need to be exactly at the right direction for the wind. But if they wanted to screw up the performance, if they want the wind not to all be harvested optimally, they don't want all that power, they play with that angle. That pitch angle is controlled from inside here, so that they meet the wind at the wrong angle. And therefore, that's crazy, right? But that's what they want to do in order to cap what? To cap the output power, right? So that's why you will end up with a curve like this. This is a output power. The output power is small, almost zero when you are less than the cut-in speed. There's a minimum speed. If you are less than this, you are not strong enough to even make a smooth. And then we start extracting power, but the wind does not have that much power to start with. So even with my maximum CP, I'm not getting my rated power. And then as the wind increase, that output power should have gone all the way up like this with V cube. But because they have rating for everything on the plate and the torsion and how much the generator can handle, they want to stay at that rated power. So once you hit the rated power, you don't want to increase. And that's why you will see how the CP is actually getting worse and worse because of all that control. They switch the plate so that, yes, that's wind, but we don't want. All right? Until you hit this, which is the cutout speed. So there are 3 speeds here. Cut in, rated, and cut out. Anything above cut out is too dangerous to be in that wind, so they park the plate, switch the angle, and basically the thing does not rotate anymore in hurricane and tornadoes, and right? So that's the cut out speed. And this is the rated, and this is the cut in.
Where's the cut out speed? I can't really see your mouse on there very well.
Yeah, why? Wow, so small. Right. So this is the rated, of course, right?
17.
Yeah. At about maybe I would say 14. Maybe 14.
Okay, yeah.
Maybe 14 is rated. And the cutout is the end of that graph at 25.
Oh, it's the 13.
The cut in is when the numbers start moving. It's really hard to tell from the curve, but this curve is actually what we have in our lecture notes. It's this particular turbine. So if you notice that it's the same, you would have opened that table, and that table will tell you exactly what is the cut in, which is 3 meters per second. And you look at where does the power hit its rated power, which is like 13. But I mean, I will make sure that Tawheed know that it's really hard for you to read from this graph. So he should be really nice, you know, when it comes to those numbers. Yeah, right. Yes. That's another way to do it too. If you click on over here, you will find the turbine file and the power curve file. Right. Say that again. Right. Yes. Yeah, I was very happy to find this and give it to you in the. So we can see that there is over here the cut in, and you can see the rated, right? And you can see the cutout. Okay, good. So what does he want from us? Please find the turbine power output and CP when the wind is this, and this. So all you need is just read from the table, right? And get the power and get the CP. But I just want to make the point that this way of presenting things when you have 2 y-axes is super easy to do it in Excel. And you should remember to do this in your presentation for senior design project. It's so cool, you know, when you have 2 phenomena coming on 2 different y-axes. I think, and that not that many people do this. They just have one graph after the other. But when you combine 2 things, I think you drive the message better. It's better visual for your presentation. Okay. So now if the annual wind distribution in the site at the hub height is as follows: 2 meters per second, 400 years. 400 hours, 4,000 hours. So what this mean? At 2, you will not extract anything. So for 4,000 hours per year, 0 output, nothing. You will not get anything. And then 10 meters per second, which is here, which is 250 kilowatt coming out. This will last 2,000 hours per year. So if the power output is 250 and this lasts 2,000 hours, how much kilowatt hour we get? Multiply the kilowatt times the hour, you get the kilowatt hour from this wind speed, right? And then 50 meters per second, which is above the rated, which you get the rated power for this much, the remaining of the year, because we know Total number of hours per year is 8,760. 8760. Wow, look at that. It's amazing. 8760. Someone is looking up for us so that we wouldn't really have to suffer. 8760. It's like Stephen Constant too. 5.67 to 10 to the power minus 8. What is 5.67 10 to the minus 8? How amazing is this? But I mean, they screwed up in Avogadro's number because I cannot remember 6.022 10 to minus 23. That is. I mean, I struggled always to remember that 10 to minus 23. Anyway, point is, the year is divided into 3 velocity, and for each one of them, from this curve, we can figure out what's the output power. So when he asked it, how much is the annual kilowatt hour? What do? You will basically say the output power would be this much times 0 times this much times this much. Okay? Now, he said that there is not one turbine. There is 356 wind turbine. Okay, so I was trying to mock up that big wind farm they built in Oklahoma, which is supposed to be the largest on one site wind farm in the USA, mainland USA. No one ever had like put 998 megawatts of turbine at the same project, at the same site. So if there are 356 wind turbine in that place, what is the farm capacity factor? What's the capacity factor? That produced divided by maximum possible. Okay. So the produced will be 356 times how much each one of them is making. And then the CF would be this that we just calculated, kilowatt hour divided by the maximum possible. Maximum possible is B rated time the number of hours per year. So that capacity factor is 0.485. If you go to their webpage, you'll find out that they actually say their capacity factor, but not with, of course, this is not really a real number. I mean, 4,000, 2,000, and that doesn't come like this. The wind come with a curve, and we will deal with that curve today, right? But when they did it with the real curve, they figured out that their capacity factor is 0.4 something, 0.43 with the actual wind. Okay, so and that calculation is done exactly like we did, but not 0 and 10 and 15. No, it's 0, 1, 2, 3. For every single velocity, they would say how many hours per year, what's the power of the turbine, and they do that calculation. Okay? So you need more refinement than this. So any question about what is the CF and what's the CP? Very clear. All right. Now, the second one, he said that sometime we get the data at 20 feet, like this table. The whole table is done at 20 feet, but the turbine is sitting at 85 meters, right? And the first thing is, can you give me that table at 85 meters? And we said the only thing that will change at 85 meters is not the number of hours and their direction. What will change is only the velocity. So when it's 1.5 at there, up there would be higher. So all we need to do when he said, give me a new table at 85 is just change this, right? So when I change that velocity, the 0.5 become 0.8, the 1.5 become 2.5. So those numbers from 0.8 to 16.9 will replace those numbers. Same table, but just with different label. Make sense? How did I make that jump? That equation. U over U is Z over Z to power alpha. Good. So now the second part, he said that turbine will not give its rated power unless the velocity at the hub is 10 meter or higher. So at the hub height, the velocity here is 0.8 for this many hours. 2, 4, 5, 7, 9, all those hours, the turbine is not running at rated power. Only when it is 10 and higher, which is this. We said how many hours are that. So we just have to figure out how many hours per year will the wind stay in that category. It's actually those guys. At 20 feet, when it's 6 to 9 to 10, if we add those guys, it's 827. So that's the number of hours where the velocity at the hub will be 10 or higher. Okay? So that was the two problem in the homework. Question about this. Piece of cake, right? Very good. So let's take a 5 minutes break and I will start. I'll finish the wind chapter and then we can practice a bunch of review problem. So 5 minutes break. All right, I think we should start. So we said that the turbine will have those characteristics, this curve, which basically say you kick in at V cut in, and then you will rise, not really in a straight line, but more like a curve until you get V rated, and then you will continue until V cut out, and then after that, you stop making power. So this is B output. Okay, so this would be B rated. So to figure out how much energy kilowatt hour we are producing, we need to figure out what is that site statistics. We need to know how many hours per year you're gonna be without any power, find something else. How many hours per year you are in this range? Because even in that range, you bought like a 3 megawatt wind turbine, it's not producing 3 megawatt wind turbine. So you are not getting your rated power, right? So if this is an island of the coast of Europe in like Scotland or something, and this is all their energy, and they think they have 20 megawatt of turbine power, no, in all this range, they may not have the rated power, or even worse, they may not have any power, right? There's a hospital or something, the guy will die because there is no electricity coming to the hospital at that time. So in this range, what will happen? So in this range, you can tell yourself, I can live if I have more turbine than what I needed. So what do you mean? Like I want 10 megawatt for that city or that village. Okay, buy not one turbine, buy 3 of those turbines. So that if they are all of them are producing 1/3 of their rated power, you will be able to still get the full load. And anyway, you're gonna buy more than the rated power. Why? Because there's something called CF, right? So with the CF, it means that you are not gonna get 3 megawatt all year long because of the wind characteristics. So if the CF, let's call it 0.5. Let's call it 0.5. That means if you want 10 megawatt in that place, buy 20 megawatt worth of turbine. So this way, at the end of the year, they will produce as if there's 10 running all year long. That's the mean of CF. The actual divided by the maximum possible. Yes, so if I ask you to specify for a place they really wanted to have 10 megawatt all year long, and that place have a 0.5 capacity factor, and that capacity factor, you can notice that it's not just the site that's responsible for that CF. It's the matching between the two of them. Like you are good by yourself, your partner is good by themselves, but both of you together, you are horrible family. You're not compatible, right? Wind turbine is amazing. You have really good. The site is pretty good, but it's not for that kind of wind speed. Right? There is always wind, but always at 7 meters per second. And that turbine kick in at 7 meters per second. 0 power out. Right?
So the CF isn't a characteristic of the site itself, it's a characteristic of the wind also.
It's multiplication of both of them, right? So just like that homework problem that we just did. I mean, we calculate the CF from the actual power. How did we calculate the actual power? It's the number of hours you stayed in that wind category times the power at that from that turbine at that wind category. You multiply two numbers. Site available turbine produce enough power at that place, at that wind speed, right? So what I'm saying is that if this is B load and this is the 0.5, then the B installed should be the B load divided by the CF. Make sense?
What's the handle that?
If B load, if you want to run 10 megawatt all the time, the load is 10 megawatt, you wanted to, they told you, we want 10 megawatt from that wind all the time, right? And you know that the CF of that place is 0.5. That means each turbine, I buy a 3 megawatt turbine, 10 megawatt turbine, worth of turbine, they will only produce half of that power, right? So I need to, how much should I install? If I want to guarantee 10 megawatt, the B load divided by the CF. Okay, that is B installed. That's what you will tell them we need to install. Huh? You build twice as much, or like if that CF is 0.3, it will be 10 over 0.3, right? So at the end of the year, you tell them, see, I gave you 10 megawatt. Of course, unfortunately, that 10 megawatt is not gonna be every single day. Even worse, not every single month. That CF, when we calculated that CF, when we calculate the number of hours per year, the wind stay at B rated or higher, maybe those are the summer months, not the winter months. So wind energy doesn't run by itself. You need always energy storage. Yes, it will, if you count for that CF, you will get your 10 megawatt at the end of the year, right? Because we installed 20 megawatt and he's running with 0.5, we will give you 10 megawatt at the end of the year. But no one said that we'll give it to you every single day or every single month. But we will give it to you at the end of the year. So get your lake on top of the mountain so that you can store or buy batteries so that you can store from summer to winter. I don't know how many batteries you need to store the wind in the summer for the, right? So that's the problem of depending totally on wind energy. You need to make sure that you're in a place where the wind is uniform every single day, and during the day it's constant. If not, if you go up and down, you need to store that extra so that you can supply the main. And if it's summer months and winter, see how much you are above in the summer and make sure you store that for the winter, right? Or make sure that your energy budget include other stuff beside the wind, right? So that you wouldn't be like that guy in the control room when he was telling me, see, the wind was running before the people turn on their coffee maker in the morning and now there's no wind. Yeah, you need to know that it's gonna fluctuate. So store it in something else. Right. So if we talked about this and how the plate angle is adjusted to get the V absolute, and that's the mechanism, right? To control it, to control the angle of the plates. And so the cut in speed and the cut out speed basically tell you how much of the energy, this is over here, this is energy of the wind. How did they get the energy available in the wind? I know the power available in the wind. If you give me the velocity, that's the velocity is like 15 meters per second, for example, I can tell you the power. How? If the velocity in the wind is right now 15 meters per second, how much power is available for that turbine to harvest? The power would be half rho A B cube. So that 15 will come here. That area is the swept area, right? And rho is 1.2. So that is the power. But how much energy? And the unit, of course, is watt or kilowatt or megawatt, right? But how do I calculate the energy at 15 meters per second? Help. If the wind is blowing at 15 meters per second at the hub, the power available for that turbine is half rho A V cube. V is 15, A is the area, rho is 1.2. But how much energy is available? How many joules or kilowatt hour? So the energy here should be in joule or kilowatt hour. How do I calculate that? So I can come up with that graph. The hour at which the wind stay at 15 meters per second, right? So the energy is power multiplied by the time. So for every one of those category, every one of those velocity, there is power and there is energy. And the energy is not just the velocity, it is the time at which it stays. And so that's why, I mean, if we just plotted the power, the curve will go like this, of course. Half rho AV cube will go up like this. But what make the curve of the energy go down is because what? At those high velocity, it doesn't last that long. Not that many hours per year is the velocity is 50 meters or 45, right? Those are like the 2 tornadoes that we get per year. Yes, the velocity is super high, but the time is super small, and that's why the energy get lower. And that explained to us what? That explained to us why there is a cut-out speed for the turbine. If we want the turbine to harvest all that velocity up till here, you have to have better material and you have to have amazing design. For what? You know, why would you spend all that expenses just to harvest this part? Maybe that comes with really very expensive price. So you tell yourself, you know, this is good enough. Between cut in and cut out, I will be able to harvest all those kilowatt hours. Right? So I guess what I'm saying is that at very, very high velocity, don't feel sad. What? The turbine has a cutout of like 20 meters per second. What happened? Like we get 21 and 22, that's a lot of power. Yeah, a lot of power, but not a lot of energy. Right? Because the number of hours, so it's not worth it to make it work that far. Okay. Right. So this graph is just showing us how that with the variation of the wind speed, the angle of the plate keep playing so that he makes sure that he have a constant power output. Right? So he play with his CP so that you go up, you go down, I make myself do better, do worse so that I can guarantee my rated power. Of course, that above V rated. If you are less than V rated, whatever, you cannot do anything. You will get less power. But above V rated, you can sustain that power up. So you get that curve, right? Make sense? So cut in, rated, cut out. So, and so in the real curve will be like this. Yes, that's the one that we use in our homework. And so in all those things, we always wanted to know how many hours per year is the velocity this much so that we can get the power of the turbine. So the way that I gave you in this homework problem, that's for simplicity, right? But for an actual site, it's not gonna be 0, 15, and 20. It's gonna be continuous wind. So it's gonna come in a table like this, right? Table with number of hours for every single velocity. Okay. So how do we represent this? I mean, if I plot this, I will get those data points on Excel. I get those guys, and they are discrete. So now in order to be able to compare different model, like this turbine or that turbine, which one will do best? You need to calculate the actual output, actual energy output from that turbine on that side based on that table. So you can do it row by row, or even better, if you can have what? If you can have a curve, if you can have the equation that represents that curve. Like, we need the best fit curve for those tables. So they did this. They actually figured out what is the best fit curve for wind data. Okay. Two of the most famous is Rayleigh curve. And that Rayleigh curve is a special case of a more general curve. It's called the Weibull distribution. So that Weibull distribution is going to be in our midterm next week. So we need to look up, and it will look scary, but I'll show you that the way that I'm going to ask you about is going to be very simple and it's doable, right? But we need to understand how do we deal with this curve, because it's really useful. It's very useful to deal with a statistical curve for any application later on, whether you're going to work in wind energy or you're going to work with strengths of material or welding or whatever. A lot of things come with a distribution, and we need to learn how we deal with those distributions. So this curve has x-axis, that is the velocity, right? And the y-axis is describing the probability of that velocity. So when for example, this becomes like 0.1, that means 10% probability of having that velocity. So for every velocity, you can go and read the number, right? Except that it's continuous curve. So it's not really like when I read at 20, it's the probability of exactly 20. Not 20.1, not 20.2. Right? Because it's a continuous curve. And it's described by this equation. So you can see that it has two knobs, two parameters, the K and the C. Okay? The K and the C. Those are the two numbers. So people that get the data from the site, they play with different K and C until they figure out what is the best K and C that represents Oklahoma City or Tulsa or Denver. Then it's a perfect match. And then now they have the curve that represents that city. Okay? K equal to, that is exactly what the Rayleigh curve is. So the Rayleigh curve is a Weibull distribution with a K equal to. But so that tells you that K is most of the time near 2. That's why they came up with that Rayleigh distribution. But learning how to deal with those numbers is more useful because it's more uniform, more general. Okay. So K can be any number, but most of the time it's very close to 2. And C is the scale parameter, and it's in meter per second. And so you can tell that C will move the peak of the curve, and the K will flatten the curve or will spike it with those two numbers. Okay. So like here, look at this. Here is K3, here is K2, and here's K1. So with K1, the curve is flat. K2, K3 is more spiky. Okay? And so all those were done with C equal 10 mile per hour. You can see here is the 10 mile per hour. So C is not the peak, but it's the number that will move the curve. Will move the peak. But it's not exactly the mood. It's not the maximum point, but it's nearby. Okay, so what is the big deal of having the distribution, the Gaussian distribution of the class, or the Gaussian distribution of our weight? Okay, what do you do with distribution? Distribution of any function, that's the maximum information you can have. It's like really great. You know everything about that population. Okay? When you know their distribution. You can figure out if you have distribution of income in the city, we would know exactly how many are under poverty, how many billionaires we have, how many middle class, how you can get all the information, not just the average. You see, if I have the distribution of the fuel coming from my injector downstairs in the lab, I know how many droplets are big enough that will give me soot and the combustion will not be clean, and how many will be super tiny that will not even make it to the main engine because they are super small, they evaporate, right? It's really good information. So what information you guys want to get from this? I would like to get the average velocity, of course, right? And that is a question in the exam. I'm gonna give the distribution. I'll tell you Weibull distribution with that K and that C. And let's find give me the average velocity in that side. That's one way to ask about. Okay, how do you get the average? So by the way, this is the effect of the C. As C change, it take you to higher location, right? So how once you have a distribution, how you get the average? You do this. And this is for any distribution. If it's Gaussian and you want to get the average, if it's Weibull, if it's Rayleigh, if it's once you go to grad school, there is so many distributions for other stuff. Rosen-Ramler, Maxwell-Boltzmann distribution, every distribution describes something that in physics. The way to get the average for all of them is to multiply the distribution with AV. What do you mean? Well, that's the K over C multiplied by VC. I'm just bringing it from here up here. V over C, K minus 1 multiplied by E to power minus V over C to power K. So make sure you can read this. I mean, what is that? That's E to power. Exponent, that means E to the power. Power what? Power what's inside this bracket. What's inside this bracket? There's minus sign, and V and C are raised to power K. So E to power, and the number on top has also another power. Power. Okay? So that is the distribution. Now, if I multiply this by V, then what I did is HV multiplied by V. And then I integrate from 0 to infinity. That will be the average. So now you would say, well, he's crazy. He wants us to integrate this in the exam without computer, and we are doing it by hand. And the answer is yes. And the answer is that this is actually very easy. How integrating this is easy. So this is a part that I would like you to make sure that we totally understand. How we integrate any function. So, you know, integrating those things you need a table, right? Because not that many people remember that the integration of cosine x is sine x. And if it's like cosine ax, you know, like you divide over an a, and the integration of e to the power x is e to the power x divided over 1 over a. We need table to remind us of this. And when things become a little bit complicated like this, you need to remember the method that, well, let's integrate it by parts, and let's differentiate the first and integrate. It's a mess, and we don't need all this to do it. There's something called numerical integration, and you probably remember it from 3013. Did we had 3013 in this? We did, right? Everyone here at 3013? Yes, engineering analysis. And there was numerical integration part. And that numerical integration is the same way you do it, whether it's sine x ax or k over c to power v exponent e minus v, whatever the function, it's the same method. What is it? It's basically saying that when you are integrating a function, and that function look like this, like our distribution. Is that f of v, and described by that weird k over c, v, and e to minus v over all this stuff, just any function. What is the meaning of that integration physically, or like on this graph? It's the area under the graph. It's the area under the graph. And if we can measure that area under the graph, we don't have to get all those tables. Forget about all those tables and sine, this cosine, and okay, how do I get the area under the graph? I know the area of a rectangle. Good enough. What's the area of a rectangle? It's the height, let's call it b, multiplied by the base, h. That's the area, ph, right? So if I divide this into 4 parts, let's make them 4 parts, right? And basically tell myself that I'm gonna measure, get that volume, that area, and that area. Those 4 guys. How do you calculate the area? Height times the base. Well, the base is, I'm gonna go every 5 meters. So from 0 to 5, 5 to 10, and 10 to 15, and 15 to 20. So the base is always 5, 5, 5, 5. So that's how we're gonna make it easy for you in the exam. I'm gonna tell you, get the average using, rather than the distribution is like 14 parts, I just will tell you use just 4 parts. So that's the step size. This is the h, basically, the base. So use delta v equal 5 meters per second. That's the delta v. Yes. I can't hear. So this is, first of all, this is numerical integration, and that numerical integration, this is called the rectangular rule. There is a rectangular rule, which is the lowest accuracy, but it can really improve if you make it very small delta v, and then there is trapezoidal method, and then there is Simpson rule. So the difference between all those guys is that one of them is dividing this into rectangle, which you can see it's not that great approximation. The other one basically say that in every one of those sections, we have a trapezoidal. And so you can immediately notice that, wow, this is actually more accurate. And funny enough is that all it takes is the difference between those guys is that this is the height multiplied by delta v, but this one is, how do you calculate that area? It's the average height multiplied by the same delta v, but the average height requires you to get the first and the second. So it's a little bit more complicated, tiny bit, but we will stick here so that I wouldn't freak you out. We'll just stick to the rectangular rule, good enough for us, right? Of course, the Simpson method, so one was constant, the other one is linear, and the Simpson method will, what do you think will happen? So constant, linear, a second order curve. So basically it used every 2 points to fit a second order, which make it like really, really good approximation. It's amazing. And it's not like you're gonna come up with the equation yourself. It's, when you add them, it's like the first and the last, and 2 times the odd plus 4 times the even. So all of them is like just different formula, but we will just learn the easiest one. And so why do I insist in doing this? Because I think you should never leave college without learning how to numerically integrate any equation, okay? This is a very important tool. Like you left high school knowing how to adding and subtracting, you should leave college knowing how to integrate any equation. And you should leave graduate school. I was having this discussion this morning with my graduate student. Solving ordinary differential equation. In our research, we had a bunch 3 ordinary differential equation that we have to solve them together. And I was like telling him, you have to solve this. And it's really important skill for research to solve ordinary differential equation. So in college, I think you need to be able to, anytime you see an integration, it should be super easy. And it's super easy. You'll see why in a minute. Okay, so what did we say now? We said that we just want to get the area under the curve. And if we divide that curve into a bunch of squares, bunch of rectangles, then all we have to do is delta V multiplied by the height. What's the height? Well, the function value at that V, the function value at that V, the function at that V, the function at that V, the function at that V. So it's really f of V. That is the height of the square times the base of the square. And we're going to add them. So the numerical integration, basically, you can see what happened. I mean, let me make it f of V, the height multiplied by the width. You can see what happened. The dV is now delta V, and the f of V is the same, and the integration becomes summation. So as a matter of fact, when if you remember, probably the first time you ever got your lesson on integration, someone have said that this is a small guy with a dV, and the height here is f of V. And let's do this, and do this, and do this. And so if we do enough of them, that will be area under the curve. And so what we did is f of V dV, but if we make delta V go to 0, like really tiny high, this become dV f of V from 0 to infinity. And the summation become integration. So now with computers, you can do this no matter how complicated that f of V is. All you have to do is find that function at those points. Okay? Make sense? So you are not going to have a computer in the midterm, right? But if you have a computer, I'm going here you see my velocity is going every 0, 1, right? 0, 1, 2, 3. You in the midterm will go 0 to 5, for example. For every one of them, here is f of V. How do I get f of V? Let's make it f of V. So I did it into parts so that I wouldn't get confused. So this is the VC to power k minus 1, and this is E to power, the thingy. At the end of the day, this is EF of V, right? And then what do? I add all of them. And when I add all of them, I get the average, right? So here is my f of V, and here is the V multiplied by f of V. This is the one that we are adding. And so in our book, he actually integrate this, right? So he integrate that formula in the book. Where is it? Here. So in this example that we'll solve in a minute, he actually integrate this. Here is the distribution. Here is the distribution. Here is the distribution. And he is multiplying it by V, and he integrate, and he gets 13.5. Okay? So with that Excel, you get 13.5. Okay? You could say, well, because we did it every 1, and so that's small delta V. But if I make it every 5, I still get 13.5. And if I do it every 10, I get 13.3. So if I in the exam, I tell you use delta V every 10, you will be just like, what is the probability after 50? It's like you don't see it anymore. So you just do 0, 10, 20, 30, and 40. You'll just do 4 or 5 of them, because the curve go to 0 after that. Okay? So what I'm saying is that with very small delta V, you get accurate results. But with big delta V, which save the calculation, it's not that bad either, right? And you will learn how to do it for later on for other distribution. Okay? So what exactly will happen in the midterm? How do we do this? He will say that the example will be this. It's in our textbook. Okay? He will tell you find V mean. And C is this much and K is that much. That would be the problem in the midterm. For that C and that V, find the average. You will open that example and you would write this equation. Okay? All right. But now I need to integrate this on my exam paper using the rectangular rule. So what should I say? I should say V is equal approximately. I didn't share, right? Sorry. So I was saying that this example 4.2 is exactly what I'm planning to do in the midterm. So example 4.2, where you say find V mean if C is this and K is this. This is one of the 3 problems I'm planning to give in the midterm. For that K and that C, any K and C, find V mean. So you will say, well, it's Weibull distribution, because you said, well, I'm going to say Weibull distribution with that K and that C, but different K and C, right? So you will come and say, well, here is the equation. I mean, here is the equation for any average. Any average is the probability of that variable, x dx, where this is his distribution. Gaussian, Weibull, whatever the distribution that describe him, you write this guy. Which happen here, this is the velocity we care about, specifically the velocity. So you're gonna write this. Okay? This is the average velocity. F of V multiplied by V multiplied by dV, and you integrate. Okay? And then you will write this. You replace F of V with this guy, because it's Weibull. Yes? And then what's the third step? So number 1, step number 2. Step number 3 is doing what? Is to say that V mean is approximately what? Summation of help F of V time V delta V. V delta V, right? And so that delta V, I don't know whether I should, I will tell you, right? I will tell you use delta V equal 5 or 10. Right? So that means 0, 5, 10, 15, 20, 25. And then you realize that, man, it doesn't really pay to go to 30, because when I substitute here at 30, it's like 0.001. I'm adding garbage now. It's really tiny, nothing. Okay, so how do I do this then? Well, f of 0 multiplied by 0. Time delta V, of course, is going to go to 0. Plus f of 5 multiplied by 5 multiplied by delta V, plus f of 10 times 10 times delta V. Make sense? I could keep adding, but then you realize that, well, how do I get f of 5 and f of 10 and all those f? How do I get them? Huh? Say that again. With what? With this equation, right? With this number, this thing between, this is the f of v. So you put v here 5 and v here 5, and k and c are given to you. So the way to solve this is actually you have to make like a table in the exam, in the answer sheet. You write v 0, 5, 10, 15, 20, and f of v, and that's the big equation, right? And v f of v. You multiply them together. And you finish and you add summation. This is the summation. This is the v average. Okay? Intimidating if you don't understand, you know that this is the function that you need to substitute. Right? And also because what? Because this equation is not written in the book. So you need to write this in a very clear place. That integration can be approximated with the rectangular rule as simply just delta v multiplied by f of v. And why this v is sitting over here? Because that's what the integration is all about. We are basically integrating this function. To get the average, we are integrating this function. It's not just f of v. It's not just f of v. It's f of v multiplied by v. That's what we are integrating. Right? Does it make sense? So to check on my Excel again, the function that we are integrating is really this, not this. So by the way, if I integrate this f of v, not f of v times v, an average, and add at the end, what do you think the area would be? Free homework problem if you answer this right. If I integrate f of v, not v f of v, to get the average velocity, what's the integration of this will give me? No, it's not. Because which v? No, the integration of that f of v without the f, just the integration of v, is the area under that curve. Of course, yes. But what is the area under that curve? That's what I'm asking you about. Homework problem. The area under that curve is 1. Why? The area under this curve is 1. Because that's the whole probability of every single velocity. That's the area under this curve. That's the meaning of a distribution function. So any distribution function, Gaussian, Webel, Rayleigh, the area under that curve by default is 1. That's all the probability. Together is 1. And we split them. This guy more, depending on the distribution. Is it symmetric? That's Gaussian. It's Webel. Huh? It's log normal. There is like a bunch of distribution in engineering that we use. But they all have area under the curve equal to 1. Okay? Make sense? All right. So I can ask for the average velocity, or even more important is in that homework problem, sorry, in that example, he's not asking for the average velocity, which you get it by multiplying v times f of v and integrate. No, he's asking for the average, this guy, v cubed. What is, why do you care about the average v cubed? Because the power is not just v. I mean, we are happy that v is high, but what we care about is what is the average v cubed? What's the average power we're gonna get in that site? Huh? Not the average velocity. We need average v cubed. And so one weird thing that you don't really realize is that this is not, so that you wouldn't make that mistake in the midterm. The average V cube is not what? What do you think? Is not the cube of the average. Amazingly. So you cannot say, let me get the average speed and then cube it. No, it's not. The average of the cube is not the cube of the average. So how do you get me? How do I get the average of the velocity cube? Same with the average velocity. Same with any quantity. V square, V cube, V. If you want to get average of anything, you multiply that thing with f of v, and you do the same integration. So rather than do the summation of f of v, delta v, and add, you're gonna get this, the average of v cube. You multiply v cube with f of v, and you add them. Does this make sense? Huh? So of course, then that at the end, that will be the average v cube. So then he will this quantity here, which is average v cube, if we take the cubic root of it, that v cube, average v cube, over the whole thing. If I take 1/3 of this on the calculator, I say what's the cubic root, that velocity would be the velocity that will give you the same power like the whole distribution. That velocity meter per second. So the average velocity here is 13.5. Can I use this to calculate how much power will that side provide for me? No. You need this guy. What is that velocity? It's the cubic root of the average v cube. So now that velocity, when it comes to the power, you would say it's half rho a, but not v average cube. It's v root mean cube. What's v root cube? It's the cubic root of the average v cube. So it's a velocity in meter per second, but it's coming from the average of v cube. But because the unit is meter by second time meter per second and meter per second, we take the cubic root. Yes, man. Say it again.
Yeah, it's got e effort e times effort e, so just not the last one. We also have e times effort e times e.
So the formula is f of v delta v. That is correct, right? And just I forgot because I was using delta v equal 1. You are right, totally right. It has to have delta v in it. Yes. Yes, yes. And in my Excel, I have the delta v. But the thing is, like, I divided the delta v at I did it at the end. So I did the summation, and then here at the end, I multiply with delta v. That's why I forgot. But yes, the formula, it does have delta v. You can do it here, or you can do it at the end. But I guess it makes sense. It's much easier to remember if you just put it over here too. Right? So, I mean, let's write this. So the integration is f of v multiplied by delta v, and you are summing it. If you want to take it outside the summation, that is okay. Right? If you want to put it inside the summation, that's fine too. So this is okay, and this is okay, right? And so this will give me v mean. If I want to get the v cube average, right? then I will do sigma f of v, v cube, delta v. That is the average v cube, right? And if I want the VRMC, I will put 1 over third over the whole thing. So those are the two equations we want to make sure that we have. How to get the average, V cube. Okay? Make sense? Okay. And so how those guys are not the same? Because the average of the cube is not the cube of the average. Yes. All right. So now with this graph in his hand, with that distribution in his hand, he now can multiply the wind with its time, because the time is in that distribution. That f of v is the time. So the power is half rho a v cube, but the energy will be the power multiplied by the time. And what's the time? It's h of v. But that's the probability. Well, maybe I need 8760 multiplied by h of v. That would be exactly the time. Okay? So the distribution of the energy is f of v multiplied by v cube. That's the distribution of the energy. So you can see how it is the distribution multiplied by v cube multiplied by 8760, because the distribution and the 8860, that is the number of hours you stay at that velocity. Okay? So this graph, we are not going to plot this graph, huh? but this graph, which is coming from this equation, if you have the K and C, if you have those two numbers, you have K and C, you have that shape for the site. You know how much energy is available at 50 to 40, how much energy is available over here. That graph is how much joules are available in that site at those different velocities. And so then it's very easy for you to basically say, where is the money? The money is in this bracket or that bracket. I need a turbine that will harvest this. I don't care about this much. I just care about this to this. This is where all my energy is. Okay? So having that distribution allow you to get the average velocity, allow you to get the average power, and it also allow you to get the energy available. Right? Make sense? So if the turbine is gonna run like this is power curve at those different velocity, multiplying the output of the turbine with the energy available over here will tell you how much this particular turbine will generate. Okay? And so that's what's done in this example over here. So we had a turbine that have this cut in 5 meters per second. It has this cut out of 35, and it has a rated input, what? And a rated generator input of this much. This is basically the output power over here. Kilowatt per meter squared. The maximum power coefficient is 0.5. Determine and plot the following for both systems with no control and the system control to meet the constraint. Okay. So with without any control, you will harvest the input power multiplied by the CP, right? So you're gonna, this is the CP from here to here, you are using the max, and from this point to that point, you will have to drop your CP so that you finish at this. You start here and you finish over there. Does this make sense? So until you hit the rated power, you're gonna run with the maximum CP ideally. And to finish here at that number, although there is a lot of wind energy available, you have to cap your CP. How much is that CP at that number? It's the output divided by the input. CP is always P out over B input. Right? So that's how you come up with this number. So between the max and the minimum, you just draw a straight line like this. And so multiplying that CP with that available energy, it will tell you that this is what the turbine will extract. So from here to here, you get everything is available in the wind. And from here to here, you are killing yourself by that CP, right? So that you can get the rated power. And after that point, there is nothing, right? So this is what you harvested, and this is the part that you lost because you said my generator is rated at 7 megawatt. I'm not going to get that extra. And this part is the part that you say, I'm not going to get it because I have it cut out at 35. I'm not going to get any of this. So having this curve allow you to be able to see what do we get if we make our turbine run longer. If we get a better model that can work up to 45, how much is the part that I am losing? It allows you to see what is available and what part you are harvesting. Does this make sense? Right? And you notice that this, we managed to get on this curve because all this place, we have a CP of maximum of 0.5 in this example. Right? In real life, it's 0.48 something. Yes? And over here, this again, this point, we got it just because at that speed, we only wanted that output power at rated. And we just draw the line between them. Questions? I know it's a lot to take, and we are not going to plot this curve. All I want you to be able to do is to understand that this curve of the available energy came from H of V cube multiplied by the 8760. Yes? Because this, of course, half rho. And it's because of its meters per meter squared, that's why there is no area here. Okay? So the red curve came from multiplying the distribution with V cube, and the green curve, which is like this, and this came by multiplying with the CP. So the red is what's available from the wind. The green is like, that's what the turbine will be able to harvest. Right? And you choose, once you hit B rated, you choose to say, I'm not going to get everything in the wind, so I stay at the same power up. Okay. So we are almost done. Just like to look at the future, what will happen is that you will see that how bigger turbine is cheaper. The price drop as we get bigger and bigger. So you will see them getting bigger, and you also see that we will move to offshore because it's better wind, less noise, And so you will see those big turbine, that huge plates. Like few years ago, 7 years ago or something, whenever we would go to Oklahoma City or Dallas, me and my wife, we would always see turbine plates moving on 35, back and forth. Right? And so you see those big guys. See this one, 7.5 megawatt for one turbine. Right?
How loud are those?
How high are those? I didn't sit next to one of them. And actually, I wanted to organize a trip to a wind farm over here. And the guy, kind of like made fun of me and like, what do you want your student to see? I mean, those are, you can see them from the highway. And I was like, well, I want them to talk to someone who's responsible for the maintenance and stuff. But I didn't get that close to tell you how noisy it is.
Especially the noise reduction of breaking out offshore.
Yeah, because so that people wouldn't hear it, right? Because some people complain about correctly about maybe electromagnetic interference with waves, and they say it's a little bit noisy. So I mean, if you put them offshore, all those problems disappear. Noise and eyesore. Again, I don't agree they are eyesore, but all those things will disappear if we take them offshore. Of course, one thing we need to realize that they have to be far away from each other, because the wake need to dissipate before you hit another turbine. So they take big land, right? And so when we put them offshore, also it's going to be expensive, because you want to ride cables between one place to the other. Big area with all those cables in the water, it's not going to be that cheap, right? There's even a study on about if you build a farm in Dallas or north of Dallas, how far before you go to the next farm? Not just within one wind farm, but the distance between different farms. How far before the wind is from the atmosphere come back again to the ground and it's fresh. Like the trail, the wake of the farm itself lasts, right? So here's the map for offshore. You can see how this is one velocity, but you go offshore and you completely go to different reason. It's like, so if it's good in Oklahoma and North Texas, good or excellent, I mean, I guess we are under good. You come here and it is superb, outstanding and superb. You see the key over here? Completely different scale, right? And so again, it's V cube. So you go 1 meter per second, it's a big deal. So there is a lot of potential in going offshore, right? And again, they did this already in Europe. There is a lot of wind farm off the coast of Europe, right? And actually, one guy that took this course, he was telling me that their company was working on building those ships, or helping building those ships that basically go and stand next to the turbine, and this is actually a ship. And it put their things under the ground so that it can stable itself and then rise itself, so that they can take the plates, replace the plate in the middle of the ocean, right? So they take the bad plate, replace it, or serve the generator, right? So you need a boat that come all the way so that he can replace those guys, right? And those are still, under consideration, floating. So not just offshore with a tower sitting on the floor, but maybe floating ones. And how you can make them so that they will be able to stabilize themselves in big wind, right? With the right cable, those are cheaper to make. It will not be able to bounce that far, right? And with the right weight, with the right balance, just like a ship can stay upright, those guys also can stay upright. Right? And you can see here is all the offshore wind farm already in existence, right? And we had the first one, it was like 4 turbines, I guess, over there. But they had permit for more. So we are a little beyond, but maybe because we have a bunch of winds over here too. Right? So it's all about the economics of this. Once it becomes cheap enough, we will go for it. But those poor people, don't have our natural gas and oil. So for them, that's the way to make electricity. I'm talking about Denmark and Netherlands and all those places. I mean, that's how they can get their electricity from. Otherwise, they have to import gas from Russia all the time. Right? Okay, so let's take a quick 10 minutes break, and then we will come back and solve a bunch of problems from last year.